Welcome to Module 12, Ventilation, Demand Control and Airflow Tracking. Ventilation control is not simply opening an outside air damper to a nominal position. The BAS must deliver the approved outdoor air requirement under actual operating conditions. In this module, we will review measured airflow, demand control ventilation, system ventilation calculations, airflow tracking, fallback behavior, and commissioning evidence. The professional question is simple. What outdoor air is required? What was actually delivered? And what happens when the measurement or demand signal fails? The learning objectives are practical. Learners should describe common outdoor air control methods, explain demand control ventilation and its limits, coordinate system and zone ventilation requirements, validate airflow stations and calculated outdoor air fraction, design airflow tracking for supply, return, relief and exhaust, and define fault and fallback behavior. The goal is to move from assumed ventilation to verified ventilation. The core concept is that ventilation is a performance requirement. A minimum damper position may be part of a strategy, but it is not universal proof of outdoor airflow. Actual airflow changes with fan speed, wind, filters, duct pressure, damper characteristics, and system mode. The BAS implements the approved design. It should show the ventilation basis, the measured or calculated value, the current set point, and the fallback state when measurement or demand information is not trustworthy. The hierarchy starts with occupancy state and operating mode. Then the sequence determines the required outdoor airflow from the approved design. Next, the system needs measurement or an approved proxy. The damper and fan actions then try to deliver the requirement. Finally, verification and alarms confirm whether the system is operating as intended. Demand control belongs inside this hierarchy. It can reduce excess outdoor air only when the input data are valid, and the minimum approved requirement remains protected. There are several outdoor air control methods. Fixed damper position is simple, but airflow changes as the system changes. Measured outdoor airflow uses an airflow station and a damper loop, but the measurement must be suitable for the velocity range and installation. Calculated outdoor fraction can be useful, but it becomes weak when outdoor and return temperatures are close or sensors are biased. System ventilation calculations can reduce excess outdoor air, but only when terminal and occupancy data are reliable. Each method must be documented and commissioned under representative conditions. Demand control ventilation adjusts outdoor airflow based on occupancy or a related signal. Inputs may include occupancy counts, scheduled population, carbon dioxide, access control data, room reservations, or terminal occupancy state. The sequence must define sensor location calibration, minimum airflow, set point, persistence, filtering, failed sensor response, and maximum allowable reduction. If the demand signal is missing or suspect, the system should return to a defined conservative basis, not an unknown minimum. Carbon dioxide control is common, but it has boundaries. The design must consider background outdoor CO2, occupant generation rate, sensor accuracy, drift, mixing, location, and the time lag between occupancy and concentration. A wall sensor near a door, diffuser, or occupant can be unrepresentative. A return air sensor may represent a combined area but hide individual room conditions. CO2 is useful when applied correctly, but it is not a universal proof of indoor air quality. Airflow tracking connects ventilation control to building pressure. Supply, return, relief, and exhaust flows determine whether the building becomes positive, negative, or unstable. Common strategies include return airflow set point equal to supply airflow minus a fixed offset, relief fan building pressure control, return fan plenum pressure control, exhaust measurement with supply reset, and independent pressure control for critical zones. All flow stations must use consistent units, density assumptions, and calibration. When outdoor airflow measurement fails, the sequence needs a defined fallback. Options include a balanced fixed damper position, a conservative fan speed schedule, disabling DCV and returning to design minimum using redundant airflow measurement and alarming for timely repair. The key is that fallback should not silently reduce ventilation. It should be visible to operators, time-limited, and included in commissioning tests. Ventilation commissioning must test more than one point. The test plan should include sensor calibration, minimum outdoor airflow at low and high fan speeds, demand control response to simulated demand, economizer transition, relief or return tracking, sensor failure, occupancy signal loss, trend verification, and operator display and alarm response. A one-time test at design airflow is insufficient for a variable system because low-speed operation may be where the ventilation weakness appears. This worked example shows a quality-aware dynamic outdoor air set point. When the system is occupied and zone data quality is good, the required outdoor airflow is calculated from the approved design method. The set point is limited between the design minimum and the system maximum. If the system is occupied but the zone data are unavailable or suspect, the sequence uses a conservative fixed minimum and alarms. If unoccupied, it uses the approved unoccupied requirement. The exact calculation must follow the approved design and applicable requirements. Common failure patterns repeat across projects. Teams treat damper position as airflow, use CO2 as the only indoor air quality indicator, reduce ventilation when occupancy data are missing. Ignore airflow station turndown at low fan speed, mix units or density assumptions, fail to test DCV and economizer interaction, allow fallback to remain indefinitely, or report calculated airflow as though it were a calibrated measurement. The correction is disciplined evidence, measure, validate, trend, alarm, and commission. Best practice begins with the approved ventilation requirement. Document the method. Select measurement technology suitable for the expected velocity range. Test minimum outdoor airflow at low and high fan speeds. Validate and calibrate demand control inputs. Coordinate economizer and ventilation commands so the economizer does not reduce required ventilation. Test supply, return, relief, and exhaust tracking. Make set point, measured airflow, demand source, and fallback status visible to operators. Let us summarize. Ventilation control must deliver the approved requirement under actual operating conditions. Minimum damper position is not universal proof. Demand control ventilation requires valid demand information, limits, and defined fallback. Carbon dioxide can be useful, but it is not a universal indoor air quality proof. Airflow tracking connects ventilation to building pressure. Finally, commissioning must test low speed, high speed, economizer transition, demand control response, sensor failure, occupancy signal loss, trends, and operator alarms.